This third video about the complex natural logarithm and the unwinding number gives some useful theorems about the unwinding number. So we define the unwinding number as k of z. I suppose I should use my little tentacle to point here. K of z is equal to z minus log of e to the z, which is not always 0, divided by 2 pi I. It's a bit surprising that that should be true, but we plot it and we find that it's a staircase and integer valued. So we immediately get the two results. I'll leave the tentacle behind. Z equals log e to the z plus 2 pi I k of z, where this is defined by that. It's just a rearrangement of that equation. This is another rearrangement of the same equation. Log e to the z is z minus 2 pi I k of z. This third one allows us to compute the unwinding number without taking logarithms or exponentials. All we need is the imaginary part of z. So if we take the imaginary part of z, we subtract pi, we divide by 2 pi, and we take the ceiling, the nearest integer larger or equal to that thing in the center. So that gives us our unwinding number to work with. We saw two theorems. We saw log of z1 is equal to log of z1 plus log of z2, which is what we want, but unfortunately we have to have this fix-up factor, minus 2 pi I k of log of z1 plus log of z2. This is still a useful theorem. This can give some useful simplifications. I also proved that log of z to the power a is a to the log z, which is the normal real theorem, minus 2 pi I k of a log of z. And this is true for any complex a. So what happens if a is actually a real number between minus 1 and 1, and we can allow it to equal 1 exactly? Well, if that's true, then theorem 3 here says that the unwinding number of a times log z is in fact identically 0, which is as simple as it can get. So in that particular case, if a is between minus 1 and 1, then log of z to the power a is a times log of z, always. So we like that. So in particular, that means that the log of square root of z, which is of course z to the power 1/2, is 1/2 log of z. So also in particular, when a equals 1, we have k of log of z itself is equal to 0. I'm just going to prove it for the case a equals 1, and then we'll go back and fix it up for all other values of a. So the imaginary part of log of z, that's what we need to throw into this formula for the ceiling. The imaginary part of log of z is in fact theta, where theta comes from the polar form of z. That's actually itself something that takes getting used to, but it is a very useful fact. And that angle theta lies in the range minus pi less than theta less than or equal to pi, which is our strip where the unwinding number is 0. So why is that true? Well, z equals r e to the I theta. That's the same thing as saying e to the log r times e to the I theta. So that's e to the log r plus I theta. So therefore, log of z is log of e to the r plus I theta, which is r plus I theta minus 2 pi I k of r plus I theta. And k of r plus I theta, you just take the imaginary part, that's the theta, subtract pi, divided by 2 pi. And theta is less than or equal to pi always. So pi that's less than or equal to pi minus pi. So that's always going to be less than or equal to 0. And because it's bigger than minus pi, this is always going to be bigger than minus 1. So in fact, the only thing it can be is 0. So for just the logarithm function itself, k of log of z, sounds like a weird thing to do, but it turns up all the time in here, we actually get that it's equal to 0. Now, if I run this whole proof over again with, instead of log z here, but a times log of z, all we do is we multiply that imaginary part, theta, by a number a that's between 1 and minus 1. And that doesn't change anything in there, and so the unwinding number is still 0. So there's the proof of theorem 3, that the unwinding number of a times log of z is 0, identically 0, if minus 1 is less than a less than or equal to 1. That's true for all z except, of course, z equals 0, because then log of z is not defined for z equals 0. So In particular, we have log of z to the 1/2 is 1/2 log z. But also we get cases where it's not true. So where a is -1 exactly down the bottom limit here, we have k of -1 times log of z. It's not always 0. It's really annoying that it's not always 0. This is just one of those things that you stub your toe on all the time. In fact, k of minus log z is going to be -1 if z is less than 0 and 0 otherwise. Why is that true? If z is less than 0, then the imaginary part of this is going to be I pi. And then minus of that is going to be minus I pi. And so you throw in a minus I pi in here, and throw in the imaginary part, it's minus pi. Minus pi minus pi is, gives us minus 2 pi divided by 2 pi gives us -1. The ceiling of that is -1. Bam, we get a -1 if z is negative. And otherwise, though, it works out just fine. So when we actually graph the region where the unwinding number is 0, we get everywhere except the line where z is less than 0. So that means that the log of 1 over z, which is z to the power -1, is minus log of z everywhere in blue here, but it's not true on the negative real axis. So we want to make simplifications when we work with complex numbers and complex functions the same way that we've been used to doing them in real variables. And so we'll transform log of 1 over z to minus log of z, and we may forget about the fact that it's not true if z is less than 0. And I remind you that we are dealing with the principal branch of the logarithm here. We are restricting the range of the logarithm to be this way, and this is a consequence of that. And that restriction happens in all computer programs. So we don't really have a choice about that restriction. This is dealing with life as we have it. So one other fun thing is that the log of z squared, well, that's log of e to the 2 log z. And so that's going to be 2 log z minus k of 2 log z. And 2 is not in this range. So where is that 0? It turns out that that's 0 everywhere in the right half plane and not 0 everywhere in the left half plane. And in fact, so it's true on the top part of the imaginary axis and not true on the bottom part of the imaginary axis. That fact is something that's of interest for the matrix sector function, and this defines, in fact, what's known as the C-signum function. But that's a story for another day. The problem of finding the region where log of e to the f of z is equal to f of z itself. So that's the same as finding where the unwinding number of f of z is identically 0 is really interesting. So lots and lots of different functions occur in actual practice. And if you can figure out ahead of time that these regions are 0, that can help your simplifications. And in our original paper on these things, such regions were called the clear-cut regions for f of z. And that was hat tip Samea Corliss. And of course, that's a joke. Clear-cut logs. I can hear your laughter even now. Okay, that's it for this lecture.